So we've done a couple of days of just straightforward derivatives of trig functions, mostly looking at the primary trig function sine, cosine, tan, um, and how it can be a little bit more complicated than you might think because there's the three different parts, the exponent, then the trig, then the angle. And so, hopefully we're starting to get used to that and getting better at that. Today, we're going to look at a couple of things. We are going to look at implicit differentiation involving trig functions. And then we're also going to look at, quote, properties of trig functions, which is really just the beginnings, preparing for doing sketching. So coming up with derivative charts, that sort of thing. But we'll get to that a little bit later. We're going to start with implicit differentiation. Now, for both of these things, as with everything with trigonometry, it's never quite as straightforward as this stuff is with polynomials or rationals, right? There's just a little bit more going on with trig and more stuff to pay attention to, more stuff to watch out for. We'll definitely see that in the implicit differentiation, like I say, because of the more complex side of taking derivatives of trig functions in general. But then we're really going to see it when we get to the properties. So I'll talk about that more when we get there. But it's just something to be aware of and pay attention to. So let's get started here. We'll do a few examples of implicit differentiation. You will recall that when it comes to implicit differentiation, like in polynomial functions or rational functions, there are often things like product rule that are hiding or not as easily observed, not as noticeable. And so you got to be watching for that kind of stuff. And then we also have to be aware, again, from when we first did this, of taking the derivative of a function that's in terms of y, right? And recognizing that that's different from taking a function that is in terms of x, taking the derivative of it. Okay, so this function here has a couple of parts. It's got this part here, and then separately this part here, and the right side's just a constant. It's just 0, so that should be straightforward. But what I notice about this first part is it is product rule. That's what I was just talking about, that sometimes it hides on us a little bit. Okay, so I'm going to do product rule now. And the first part is x squared, and the second part is cos y. Okay, so derivative of the first part is 2x times the second part plus, okay, and I'm going to do it this way, but then I am going to use brackets. So derivative of the second part. Now the second part is cos y. So the derivative, so there's no exponent, right? It's always exponent, trig, angle. There is no exponent. So we skip that part. Derivative, so we're doing the trig part. Derivative of cos is negative sine. So negative sine of y, because that part doesn't change. The angle doesn't change, right? That was just the trig part. Now I'm doing it times the derivative of the angle, and the angle is y, so the derivative of y is dy by dx. Okay, and then all of that times the first part, so times x squared. Okay, now I'm going to take the derivative of negative sine of x plus y. Derivative, and again, there's no exponent, so derivative of sine is cosine, so I'm still have the negative. Cos angle does not change, times the derivative of what's inside, or sorry, derivative of the angle. And this is not product rule or anything strange like that. So I'm just taking the derivative of x, which is 1, and the derivative of y, which is dy by dx. And all of that is equal to 0. Derivative of 0 is 0. So that's the first line of the actual implicit differentiation part. The rest of this still is a little bit more complex because it often just is with trig functions, but now it's just doing some algebra and cleaning it up and writing it dy by dx equals. And just like before, I might have to expand through the dy by dx and then to get the dy by dx kind of in a term on its own, factor it, move it to one side, factor it out, that kind of thing, right? So that's what we're going to do next. So I'm going to keep the dy by dx terms on the left, and anything I can move to the right, I'm going to do that. So I'm going to move this to the left, or to the right, sorry. This is going to stay on this side, but I'm going to rewrite it in a bit of a different way. Okay, and this is going to stay on this side, but I'm going to expand it because this is this thing times both things inside that bracket, right? So I'm going to expand that, and I'm going to move this first term over and just rewrite this other one. Okay, so it ends up being negative dy by dx times x squared times sine y minus cos x plus y. That's not something that that's not a distributive property thing. I'm not doing x times that and that times that, right? Because x plus y is the angle. So I can't take it out of the cos thing, and I can't distribute or anything like that. So this is cos of x plus y times 1, and then times dy by dx. That's what I'm doing right now. So the first one is just cos of x plus y, and the second one is dy by dx cos x plus y. Bring the 2x over. This is equal to negative 2x cos y. So now I can factor out the dy by dx on the left side, and I get negative x squared sine y. And I'm factoring out of this other term here as well. So minus cos of x plus y. This term I'm moving to the other side. So this is equal to, it's going to become positive. So I've got cos x plus y minus 2x cos y. Okay, now I'm going to divide. And you could be done and you could stop there. I'm going to do one more step, but this is totally fine to leave on a quiz or a test. No problem with this answer at all. Okay, you're all the way done. You've got to equal to dy by dx. And, often with these implicit differentiation questions, there's not much left that I can do with them. It would be really hard to clean this up to try to solve for 0 or something like that. So generally, we're just practicing taking the derivative and doing that little bit of algebra. Once in a while, especially in the polynomial rational ones, there's a factor that you could take out and simplify, and it's a good habit to be in, but that's not really what the big part of what we're worried about here. But what I am going to do is I'm going to factor out the negative that's in the bottom here. It's in both terms in the bottom, and I'm going to apply it to the top, which means the negative 2x is going to become positive 2x. And the positive cos x plus y is going to become negative cos x plus y over x squared sine y plus cos x plus y. Nothing, I can't cancel those or anything like that because I'm adding, so there's nothing else I can do. I can't clean this up any further. The only reason why I did that negative, you don't have to. As I said, the last step was fine to be done there, but often computer programs, so if you have a derivative calculator that you're using online or from a textbook or something like that, often they will factor out as many negatives and kind of remove them that way by applying them, factoring it from the bottom, applying it to the top, the way that I just did there. They'll often do that because I suppose it's marginally simpler than the step above, but it's definitely not required. It's just, it's one of those good things that sometimes factoring out a negative can be useful. Sometimes it is what you want to do. And so it's a good thing to be able to do. It's a good thing to recognize, but it's not necessary. Okay, let's take a look at another example. Now there's something different about this one. Cos of x plus y is something we've already seen. So let's go ahead and just get that part done. Well, we saw sine of x plus y, sorry. We took the derivative of sine of x plus y, and cos of x plus y is not much different. Again, there's no exponent here, so I go straight to the trig. Derivative of cos is negative sine, so I've got negative sine. Angle stays the same, times the derivative of what's inside. Derivative of x plus y is 1 plus dy by dx. So that's the part that we've kind of already seen, so I'm going to go through that quickly. What's interesting about this question is the right side of the equation. This is not cos times sine. This is a bit of a strange thing. This is like cos, sorry, I'll do this in a different color. This is like cos of a, where a equals sine x. Right? So A is my angle. That means sine x is my angle. That's a strange thing. I'm not sure it comes up very often in many real-world applications, but it does keep us on our toes. It's a good little thing to practice and really make you focus on thinking about when you're taking these derivatives of these trig functions, that you're really doing like forcing yourself to think about exponent, trig, angle. What is the angle? When do I take its derivative? When do I leave it alone? That kind of thing. So it really does push you into sort of being better at that kind of thing. So there's no exponent in this one, so I'm going to go ahead and take the derivative of the trig part. Derivative of cos, again, is negative sine of the same angle that was there, which is sine of x, times the derivative of the angle. And what is the angle? The angle is sine x. And what's the derivative of sine? Cosine. Now this, some people are going to think is sine squared x. And in fact, there's a habit that we have where I could see people writing it like this. And then it really looks like sine x, or sine squared x. That line is sine squared x because it's sine x times sine x. And this is just a habit of writing x after you've written sine or cosine. But that's wrong. It's not sine x. It's sine of sine x. Sine x is the angle. So you really have to watch for that. Really be careful of that. Like I say, a habit could get in the way of doing that, or just misunderstanding what the angle is and getting yourself confused and writing that as sine squared or something, or all kinds of other things can happen, mistakes that are made when our angle is another trig function. Okay, but you know, it's not really any different than if I was taking the derivative of cos of x squared, where my angle again is a function. The function in that case is x squared, and its derivative would be 2x. So I would take the derivative of the cos part, and then I would take the derivative of the angle. That's the same thing that I've done here. I took the derivative of the cos part, kept the angle the same, and then took the derivative of the angle. Right? So it's the same thing. And like I say, these are good questions to really make you slow down and think explicitly about the different parts of that particular function. At any rate, I'm going to move on here, and I am going to expand on the right side again to get the dy by dx and start moving things around, do the algebra just to solve for dy by dx. So this is going to be negative sine x plus y minus dy by dx times sine of x plus y. And again, that was just expanding that bracket. Whoops, you can't expand this bracket again like we said in the last example. This is the angle, so the angle doesn't change, it doesn't expand out or anything like that, but you can really see how trigonometry adds this extra layer of complexity and complication to these things. And I'm going to rewrite this one in a way that I think is going to be a little bit more clear. You certainly don't have to. There's no reason that I'm writing it in this order, except maybe it'll help some people kind of understand what's happening. I'm going to put brackets around both angles only. So it's cosine of x and sine of sine x, right? Those are the two trig parts that are there. And the third trig part is in the angle of one of the other trig parts. Now I can move the negative sine x plus y to the other side. and I get negative dy by dx sine x plus y equals negative, or sorry, I'm going to start with the sine x plus y minus cos of x sine of sine x. Okay, and then I'm going to divide by negative sine x plus y dy by dx, and in fact I'm going to use that negative and apply it to the top at the same time. So this is going to become cos x times sine of sine x minus sine x plus y over sine x plus y. And again, I took this negative and I applied it to the top. That's why the signs changed, and that's why the sign disappeared from from the left side and didn't go to the bottom there because I applied it to the top. Okay, but again, you wouldn't have to do that. Not worried about simplifying negatives. Obviously, if you have two negatives, you would simplify that like a monomial, but you don't have to factor them out or anything like that. Okay, so that's a couple of examples of implicit differentiation. Watch for those complicated things. If there is a situation where you have an exponent and trig and angle, then we've seen that before. It's tricky stuff. It's complicated stuff. So you really have to force yourself to think exponent, trig, angle, exponent, trig, angle. I mean, say that every time you start a question to yourself, right? And now we see that there's this other difficult kind of question where your angle might be a trig function. Imagine something like this. I'm going to come down here and say, imagine you had something like this. You were taking the derivative. So you had y equals cos cubed sine squared x squared plus 7x or something like this. Let me put square brackets around this. So I've got an exponent. Then I've got trig. Then I've got angle. But in the angle, I've got exponent, trig, and another angle. So, I mean, this would be about as complex as it gets. But you can imagine how complicated something like that would be. But if you do it step by step, none of the individual parts would be all that tricky, right? So if you just do it slowly, step by step, and force yourself to think exponent, trig, angle, exponent, trig, angle. And then when you get into the angle and you've got that again, you just start from the beginning, exponent, trig, angle, right? But these can get complicated if we want to make them as complicated as we can, kind of thing. Okay, so just force yourself to think about those and take it step by step, and watch for product rule, that kind of thing, and just be aware that it is even that much more complicated and tricky to spot and be on top of everything when it comes to trigonometry. Okay, and that brings us to our second example. And the second example is our properties of trig functions. So you notice the question says to find and classify all critical points, determine the intervals of increase and decrease. And we know if we stopped there and we didn't do anything else, if the question stopped there, so get rid of all the rest of that, then what that question means is, oh, hey, do a first derivative chart. Like, that's what that question is saying, okay? So that's what we're going to do for that part. It doesn't say to sketch or anything like that, so we're going to do a first derivative chart for that. But it's got this second part, find and classify, and then find the points of inflection and intervals of concavity. So what that second part is saying is, hey, do a second derivative chart. So we're going to do both. But we don't have to sketch, but you can see how really what this is doing is getting us ready to sketch. So it's talking about properties and that kind of thing. And this is where trig becomes all the more complex, because how do we find critical points? Well, we take the derivative, we set it equal to 0, and we solve for when it is equal to 0. Well, that means solving a trig equation, and solving a trig equation is a little bit more tricky often than solving just a polynomial equation or a rational equation. We have to think about the quadrants, cast rule, the related angle. Like we have to go back and do all of that kind of stuff because it involves trigonometry. So every little bit of this is a little bit trickier. That's why that preparation that hopefully you did will come in so handy, because when you go to solve these equations, now most of these equations are not going to be quite as challenging as the ones that we did in MHF last semester, the hardest ones that we've seen, but they do have swap outs, they do have factoring, they do have stuff going on that you have to be aware of, okay? So we're going to do a little bit of both, and because this is basically leading us towards sketching, I am going to set this up as if I was sketching. I just think it's a good habit to be in. So that's how I'm going to do it. And organization of these solutions is very important. So I would suggest you organize it the same way, but obviously different people do things differently, and it's not a sketch. So often I see people, just kind of doing it one part at a time, but I'm going to organize it kind of like a sketch because I still just think it's a good way to organize things. The last thing before we get started that I notice is it's giving me an interval, because otherwise a periodic function goes on forever and I would have an infinite number of critical points, which we wouldn't be able to find all of them. So it's giving me an interval, and it's an interesting interval. It's only 0 to pi, and it's often 0 to 2 pi. So when we go ahead and solve, that's going to be a big part of our thinking. But for now, I'm not going to worry too much about it, but it is something that you want to be aware of and notice when you get started on these. If I were sketching, I would also be doing intercepts. I would also be doing asymptotes and end behaviors, although trig functions don't tend to have those things, not the ones that we do. So there are certainly trig functions, the reciprocal functions and tangent, that have asymptotes, but we stick with sine and cosine, and they don't tend to have asymptotes, and they don't tend to have end behaviors either. So but if we were doing a sketch, we would certainly be doing intercepts, but I'm not required to do that, so I'm not going to worry about that part for now, okay? So what I am going to do is I'm going to start with the derivatives. So y prime, derivative of cos is negative sine. And that's done because it was just cos x, so that's negative sine x. Now derivative of negative cos 2x, so there's no exponent, so I'm doing the trig part. Derivative of cos is negative sine, but I already have a negative, so that's going to turn this into positive sine. So plus sine, angle stays the same, and then times the derivative of the angle. Okay, and I'm just going to rewrite this. 2 sine 2x minus sine x. Now this is where, when I'm doing sketches, I absolutely do all the cleaning up right here and get all the versions, what I've talked about in the past, get all the same versions that I'm going to need in order to solve. Sometimes when people are just doing a first derivative chart or question like this, they don't do it at this time, but I'm going to keep it consistent. So I'm going to solve this now. I'm going to, sorry, not solve it, but I'm going to clean it up so that I can solve it later. And what I notice is I've got a double angle and a single angle. And if you remember from MHF, we can't have that. We've got to have the same angle. So I've got to use a double angle formula to swap out the sine 2x. And sine 2x is equal to 2 sine x cos x. I'm going to rewrite this as 2 times 2 is 4 sine x cos x. And now I've got a common factor. So I can factor out sine x, and then I'm left with 4 cos x minus 1. Okay, and that is ready to be solved. It's factored. I can set it equal to 0 and solve it when I get to that stage of the question. Okay, but now I'm going to flip over because I'm going to need to do this later. So I'm going to do the second derivative. And I've got 1, 2, 3, 4, 5 lines here that I could choose to take the derivative of. If I chose this line, I'd be doing product rule. If I chose this line, I'd be doing product rule. Obviously, that one would be product rule. This one's just not cleaned up, so I'm not sure why I would do it. So this is definitely the one that we want to take the derivative of. And if you recall from polynomial functions and rational functions, when we did those, that was all very often the case. where we would take the derivative, clean it up a little bit, and that's the one we would take the second derivative of, the one before we start factoring, because the factored form is going to be product rule, and there's usually a version where we can avoid product rule in order to get the second derivative. So that second line is the one that I'm going to take the derivative of. Okay. Derivative of sine. So I'm going to do this part. Derivative of sine is cosine. And I'm going to do the derivative of the angle as well. So the derivative of the angle, which is 2x, is 2. And I would multiply that by that 2, and I would get 4. So I get 4 cos 2x. Now, if you can't follow that, go back and look at a similar example where we did it in fewer steps before. I suppose, actually, let me just show you above it just in case, but it was 2 cos 2x times the angle 2, right? And then this 2 multiplied by that 2 to give me the 4. That's how I would have done it. So if you want to do that in 2 steps, by all means, go right ahead and do that. It's not a problem at all, obviously. And then derivative of sine x, and it's negative sine x. Derivative of sine x is just cos, so cos x. Okay, and I'm going to go ahead and I am going to clean this one up. And I've got another double angle along with my single angle. So I got to turn the double angle into a single angle, but cos 2x is a little bit more complex. Cos 2x has 3 different versions, and we have to decide which one we're going to use, and obviously we have to remember what all 3 are. How do I know which one to use? Well, one of them has a cos squared and a sine squared. One of them has just a sine squared, and one of them has just a cos squared. All of them end up with a single angle of just x. And I want the one that's cos squared because I've already got a cos in here. So I don't want to go sine squared. If this was sine x, if the second term here was sine x, then I'd go with the sine squared one. Rarely do we swap out for the one that has both cos squared and sine squared. Okay, so y double prime is 4 cos 2x is 2 cos squared x minus 1 minus cos x. And I'm going to apply the 4 through to both things inside, and I'm going to rearrange and write it in the form that we're going to want it in eventually, the familiar form. That's going to be 8 cos squared x minus cos x minus 4. Okay, and that's as if I was writing 8a squared minus a minus 4. Right? So I put the cos x in the middle and the cos squared x in front. So it's written in the trinomial form that we're so familiar with. And now I think I got that done. I've got my first derivative, second derivative both taken and then cleaned up and fully factored because I'm going to be solving for them afterwards, right? Solving for where they're equal to 0. So let's see. I have critical values when y prime equals 0 or does not exist. Y prime, remember we always have to say this, exists for all x. It exists everywhere. These trig functions usually do. Like I said, they don't have asymptotes. So y prime equals 0. When sine x times 4 cos x minus 1 equals 0. I've already got that cleaned up. Otherwise, I'd be doing it at now. That means sine x equals 0 or 4 cos x minus 1 equals 0, which means cos x equals 1 over 4. And this is where, again, like I said, like I've been saying, trig is just that much more complicated because I'm not done yet. Now I have to go and solve both of these equations. This is a great example because it's going to show me all the different ways that we can solve, almost all the different ways that we can solve these trig equations, okay? So sine x equals 0, well, that one is going to use the graph. I'm going to use the graph for where sine x is equal to 0. And I know that if sine x is 0, then x has to be equal to 0 because sine x starts there. That's the 0 line, starts on the 0 line, crosses at pi, crosses again at 2 pi. So there's 3 solutions there, okay? And sometimes we're going to use special triangles, sometimes we're going to use a graph, sometimes we're going to use our calculator. Remember, those are the three sort of basic ways that we solve this. But there's something that I got to remember here from the beginning of the question before we even really got started. And that was the interval that this question asked us to solve on. And remember, it's just 0 to pi. So this question, or this answer, sorry, is outside the domain. So it's not one of the ones that I need. Now there's no reason why I solved to 2 pi and crossed out the ones that are inadmissible because they're outside the domain. The only reason I did that is this talking point so that we could talk about it. You generally speaking would only ever come up with the solutions. In this case, there's 2, 0, and pi that are inside your domain. There's no reason to go outside your domain and cross them out, okay? So from now on, I'll talk about it, but I'm not going to include the ones that are outside the domain. But there will be times where we are sketching or doing properties to 2 pi, and there will be times obviously where we're only going to 1 pi. Why would we only go to 1 pi? It's not something we did a lot of in MHF. We almost always were solving 0 to 2 pi. We did a little bit of negative pi to pi. But the reason why in calculus when we're sketching that we often only go from 0 to pi and not all the way to 2 pi is there's a lot going on in these functions. They have a lot of turning points, a lot of critical values, a lot of points of inflection. And if we went all the way to 2 pi, there's just too much. Our tables would be huge. All of our solving would take more time, and it's just would take too long. So sometimes with the really complicated ones that have a lot going on, we just narrow the interval that we're sketching on or doing properties on from 0 to pi just to keep it simpler. And you'll see when we do this that we're already coming up with a fair number of critical points and points of inflection. And so if we went all the way to 2 pi, it would kind of be doubling it, and that would just sort of be too much to do in a single question. Okay, so long story short, watch your interval. You only have to come up with the solutions that are in that interval. For the next one, this is not 1 over 4 is not an angle that's in the special triangles. So I am going to find x related by doing inverse cos of 1 over 4, which gives me, and I'm punching this into my calculator, approximately 1.3181. Okay, that's my related angle. Now to solve, again, if you recall, we need to do all kinds of things like the cast rule. Okay, but the other thing in this case we have to remember is that I'm only solving from 0 to pi, not to 2 pi. So any solutions in the bottom two quadrants, like 2 pi, are not needed, are not part of the interval of the domain that this question is that we're working on this question, okay? So those are out. So this was cos x equals positive 1/4, and that would be where cosine is positive. But again, these two are out. So I only have the one solution in this case. And so x equals 1.3181. If I had to go to 2 pi, remember, it would be the fourth quadrant, which is 2 pi minus the related angle. But I don't need to do that because of the domain of this question. Okay, so I have 3 solutions in the domain where I have critical values. And I'm going to write them out in order here because I'm going to need them in order for my table. And something that's really important to notice is these are the ends of the interval. Right? And when we do our chart, which we're going to do next, this is different for trig. We've not really seen this before. We sort of saw it at the very beginning when we were just on the very sort of first day where we were of Unit 3, or the first or second day of Unit 3, we sort of saw stuff like this, but we haven't seen it in a long time, so it's going to seem different. And that's just, again, one of those things about trig that is just a little bit different. Okay, so I've got my x, and we're going to do our table now. And the difference in our table is my first critical value is 0. Okay, I don't need to do x less than 0. And in fact, x less than 0 is going to go back and forth. It's going to be increasing and decreasing, because as I go back, this function is going to go up and down and up and down and up and down. So this doesn't make any sense. I'm only doing the properties from 0 to pi. So I'm going to start at the interval. The beginning of the interval happens to be a critical value, so I'm just using the point 0. When we get to the second derivative, it's going to be a little bit different, and you'll see the other way that these tables can be. So I'm starting at 0, then I'm going from 0 less than x less than 1.3, and I'm not going to write out all 4 digits, then 1.3, then 1.3 less than x less than pi, then pi. And again, I'm going to stop there. I don't have to do x greater than pi. It wouldn't make sense to do that for a trig function, but that's the end of my interval, so I'm done. Now, I'm going to be doing testing in the first derivative. I'm going to eventually be doing testing in the second derivative, and I am going to be finding y values for all of the critical points and points of inflection. And so having the original function programmed into my calculator, having the first derivative programmed and the second derivative programmed is something that I'm probably going to want to do. In this case, I've got only 2 tests that I have to do. So it's up to you how good you are at programming, whether you want to bother. These are, generally speaking, not things that you can do in your head. For instance, if I wanted to pick something in this interval, I could pick 1, and I'm going to come up to the second derivative, and I'm going to do, let's say I'm looking at this line. I've got 2 times the sine of 2, because 2 times 1 is 2, minus the sine of 1. So the sine of 1 and the sine of 2, that's not necessarily something we know what they are, because we're talking radians here. So what is 2 radians? Well, it's less than pi radians, but 2 radians is probably more than pi by 2 radians, right? Like you could kind of estimate that, but man, that's tricky. And doing 2 times one of them minus the other, is it going to work out to be positive or negative? Really hard to tell. Okay, without a ton of practice, it would be really hard to tell by inspection. So the point of the story here is you are going to be testing these on your calculator to figure out what the answers are. So I'm going to pick a value in this interval, like 1 or 0.5 or something like that, and punch it into my calculator. Now I've already done that, so I'm going to write these out, but you can try them on your own for practice if you like. And the first interval was positive, and the second interval was negative. And the other points, obviously, is where it's 0. So I've got a horizontal tangent line here. I've got increasing here, another horizontal tangent line, decreasing, and another horizontal tangent line. When you have a horizontal tangent line, you've got 2 options. You've either got a local max or min, right? So you got a turning point max or a turning point min, or you've got a horizontal twist, right? You've got a cubic twist kind of thing. If it changes from increasing to decreasing, or decreasing to increasing, that means you've got a turning point. If it doesn't change, if it's increasing before, then 0, then increasing after, I hope you can follow me there and you're visualizing this. In fact, let's draw it. Why not? I'm increasing before, horizontal, increasing after is a twist, or decreasing before, horizontal, decreasing after is a twist. Okay, or I'm decreasing, horizontal, then increasing, or I'm increasing, horizontal, then decreasing. Right? Those are all your options. So you've either got a turning point max or min, or you've got a horizontal twist. So this one's changing from changing from increasing to decreasing, and it's increasing, then it is 0, then decreasing. So this is a turning point with a max. Okay. These other two, I don't know. I don't know if it's changing from increasing to decreasing or decreasing to increasing or not changing at all. So I don't know if it is a horizontal twist or if it's a turning point, but I don't really care, because even if I was sketching, all I need, if I'm coming to the end, okay, here's my graph. And if I'm coming to the end of my graph, I'm going to go like this. And sure, I might be going like that, or I might be going like that, but it doesn't matter because I'm not graphing that part. I'm not sketching that part of the function anyway. Okay, so two of these we don't know. We can't classify, but we don't care. Okay, we don't need to. I don't know when the next critical value is, so it would be even dangerous to pick something to the left of 0 and test, because we can't be sure it would still be in the interval, because we don't know what the next critical value is. That being said, if I pick something really close to 0, there's a good chance that there's not a critical value in there. These functions do tend to be symmetrical in some ways. So if I picked negative 0.1, there's a good chance that I'm in that interval. But anyway, it's not something that we do, so I'm not worried about that. Okay, so I'm done with that. So all I have is this one. It's a turning point with a maximum. And this is where I'm going to punch it into my calculator to find the y value, and it works out to 1.125. Okay. So that's that. That is our critical points classified in our intervals of increase and decrease. Now I'm going to go back over to my second derivative, and I'm going to find my points of inflection and my intervals of concavity. So I have already cleaned that up and factored it, or not factored it quite yet, but got it as far as I can go. In fact, I didn't factor it because it's not factorable, because when I do b squared minus 4ac, I get 129. Okay, so it's not factorable, but it is solvable because the discriminant there was positive. Okay, so for possible POIs, they occur where the second derivative is equal to 0 or does not exist. Okay, second derivative exists for all x. Where is the second derivative equal to 0? So that is where cos squared x minus cos x minus 4 equals 0. Again, the discriminant tells me it's not factorable, but it's solvable. So therefore, cos of x, remember it's not x equals, it's cos of x equals negative b, so b is negative 1, so 1 plus minus the square root of 129 over 16, or 2 times a, 2 times 8. So cos x equals 1 minus root 129 over 16, and cos x equals 1 plus root, 129 over 16. Okay, and I get cos x is approximately 0.69, and cos x is approximately negative 0.65. Okay. Sorry, that was wrong. I wrote the wrong one there. That should be 0.77. If you're checking that on your calculator, I misread that. That should be 0.77. Okay, so I've got two solutions. That's just cos x. We need to find x. So x related, punching this into my calculator, this is the 0.69. And then x related here, remember you drop the negative when you're punching this into a calculator. So you would just do shift cos of 0.65, or actually I would use the exact version in my calculator to do this. And x related is 0.87. Okay. Again, this is 0 to pi, And so cast, but I'm not using the bottom two because it's only 0 to pi. So this one was positive, so quadrant 1. So I'm going to have one solution, which is just the quadrant 1 angle. But this one was negative. Okay, so I need to use the related angle to figure out the negative one, and cosine is negative in those two quadrants. So this one is going to be quadrant 2. Okay, so my x in this case is 0.69, and my x in this case is pi minus 0.87. Again, I would use the exact value here, and that gives me 2.27. Okay, so I've got two answers again here for this, for the second derivative within our domain. I'm not solving all the way to 2 pi and canceling out answers. There's no point. It's a waste of my time. Okay, so I've got x. Now notice I don't have the ends of the interval for this one. So what I'm going to do is I'm going to start at the beginning of the interval, less than or equal to x, less than 0.69. And I can be confident that there are no other points of inflection or possible points of inflection in this interval because they would have come out when I did this solving. So I know that I can go from this first one all the way to the end of the interval, and I know that within there aren't any other possible points of inflection. After there will be, so that's why I have to stop at 0. Okay, then I've got 0.69. Then I've got 0.69 less than x less than 2.27, then 2.27, then again 2.27 less than x less than or equal to pi. Second derivative, and I'm going to do the same thing, and I'm going to program it into my calculator so I can just punch in the values to do the testing easily. Or again, there's only 2 tests, so maybe you just type it out. That's up to you. That's part of while you're practicing. Actually, sorry, there's 3 tests in this case, so maybe it makes it more worthwhile. But when you're doing the practice, that's what you have to decide for yourself. Which way do you prefer to do it? Okay, so I know that the second derivative is 0 at those 2 locations. When I do the testing in this first interval, I get positive, then I get negative. In the second interval, then I get positive again using my calculator. So this is concave up. This is concave down, and this is concave up. We haven't seen this yet. We call these possible points of inflection. I've said this before, but we call them possible points of inflection because sometimes it doesn't change from concave up to concave down, and there's just nothing happening there. And we think that there should be something happening, but there isn't. Okay, so I have to check, but in this case it is changing. So both of these are points of inflection because it changes from concave up to concave down, and this one changes from concave down to concave up. That's what a point of inflection is. Okay, and so this is a point of inflection at 0.69 and 0.58. And this is a point of inflection at 2.27. I had to find the points in the question, so I do have to do this part. And again, I'm punching these values into the original equation, which again, I probably programmed into my calculator because it makes it a lot easier to find all the different points that I have to find. Okay. And that's done. That's the question done. I'll do a quick sketch just because we've got the time here and we've got all the information. I'm just going to do a rough one. I'm not going to do a full sketch, but that is where this is going, so why not? But otherwise, I'd be done. I found all the points of inflection, and I found the intervals of concavity, and I found the intervals of increase and decrease and the critical points, and not just critical values, critical points. I found the y values as well. Okay. When we sketch, the other thing we often add in here is where the start is and where the end is. So it starts at 0, 0, and it ends. So here are 2 more points that I'm punching into the calculator to find the y values of. When you're doing a sketch, you have to do that. Okay, so there's at least 5 points where I subbed in values into that original equation to find y values given an x value. Okay. And let's see, I would be doing A, B, C, and then maybe even D, or maybe I would even label the start as A. But I'm starting at 0, 0. I'm going up to a turning point max at 1.25. I'm crossing down and I'm ending at -2. Now, there's a lot of different things that go into this. Sometimes we label pi by 2, pi, that kind of thing, but often because we have decimals, it's actually easier to label 1, 2. These aren't going to be very well spaced. I'm going to move this one. So I'm going to label it as 1, 2, wait. I'm going to put 2 here, move this one over a little bit. There we go. And then 3. Oh, I'm messing this up. Okay, this is just after 3. So 3, 2, 1. Try to evenly space those. 1, 2, 3. That's better. Okay. Because this is 3.14 where the end point is, right? So my first point A, which is a turning point with a max, it's actually not my first point, but it's just after 1, so I'm going to put it right about there. And I've got a POI at 0.69, so that's going to be somewhere in here. Okay, I'll do that one after. And then at 2.27, I've got another POI, so I'm going to watch for that. So I'm starting at a horizontal tangent, and this is a concave up region. Changes to concave down. There's my max. Okay, I've got an x-intercept in here, obviously, somewhere. I'm concave down, somewhere around 2.27, so somewhere around here. I change to concave up. Let me try that again. And then I have another horizontal tangent line there. So I've got my point B here. Sorry, that's C. This is A. This is my B. There's my C, and there's my D. Okay, and that's at pi and at -2. And that's at 1.125. Anyway, that's good enough for now. So that's what that looks like, and that's only half the curve. So you can see that these things have a lot of stuff going on. But that's properties of trig functions, which is really just the beginnings of sketching. And then as well, we did some implicit differentiation, and all I can stress is that it is that much more complicated when we're talking trig, because there's so many other little details to pay attention to when we start solving with the cast rule and all that kind of stuff. And just taking derivatives is a little bit more complex, even though derivatives of sine and cos are so simple. Once you start adding exponents and angles, it becomes tricky. Okay.